Hello, good morning, everyone. I'm Lieven. I am, let's say, a replacement of some people who could not make it. So this is probably the least prepared presentation of the entire conference. So I can win a medal. C++20, we all know the big four concepts, coroutines, ranges, and modules. There are also a bunch of little useful things. One example, on a map, you can now say contains, and the intent is clear. No need to count and see if the count is bigger than 0, or do a find if and see if it's not cent. And one of those is also the spaceship operator. We will see it looks like an easy thing, but it is C++20. We need some hidden complexity after all, or it's not a good feature. We will start with a little interactive session, so I need your help. Shout out the answer if you know it. Who are these? The Jackson 5, that's correct. Who are these? The Bee Gees, yes. These guys? Oasis. Yes. Oasis. Janet Jackson. And we have one more. There is a pattern. Maybe somebody already noticed the pattern. No? Kylie and Danny Minogue. Who discovered the pattern? Nobody? They are all siblings. In music. Siblings in music. Now, we are starting a new company, or we're a consultant for the music industry. They asked us, we have a big database of siblings in music. And in that database, those siblings are stored with their surname and first name. Their database is a vector. They couldn't afford a real database. And they have a problem. They were entered random order. They want us to sort this thing. That's our job. So, you see there the database. Our solution, we will sort ranges, we will print them out. It does work. And this is how we make it work. We had the struct of the siblings in music with their surname and first name, and we use a spaceship operator. As easy as this. We solved it. Great. That's it, folks. It's as easy as that. Well, maybe there are a few things we should have a closer look at. Operators. We have two sets of operators. We have the equality operators, is A equal to B. And we have the relational operators, is A less than B, less or equal, and so on. Now, in the past, how did we address this, or which kind of problems did we encounter? Let's assume we have a magic int class, which has an implicit constructor, which takes a regular int and puts some magic on it. Now, the magic is top secret. That's why the magic is not on the slide, and we only see the bare minimum part. So we had to implement the equality operator, which is a constants operator, and returns a bool, and we just say, hey, is my stored int equals to yours? And we return yes or no. And we also provided the less than operator. Simple implementation. We did not provide less than or equal, and so on. Maybe we need it, maybe we don't. With this, we can already check for equality, and we can already sort. The sorting algorithms are happy with this. So that's great. However, when I compare an instance of the magic int with the magic integral number, 242, it works. When I do it the other way around, it doesn't. That's a bit strange. We all have a mathematical background, or most of us, and we know if A equals B, B equals A. Here it doesn't. So we need to solve this problem. Now, why this one work? That's because it's an implicit constructor. And the 2 for 2 was converted by the compiler into a temporary magic int instance, and then the comparison was done. But an integral, it's a system type. It doesn't know how can I transform myself into a magic int, or your int, or a better int. So that doesn't work. How did we solve this in the past? The past, I assume also the current. We provide an extra method, inspired by mathematics, and also, as Scott Myers always claimed to do, if you write your own type, act as an int. So it means we need the symmetry. So we use a free method. We add a free method which swaps the operands. So when we do equality on an int, our 2 for 2, and an instance of our magic int, we say, you know what? Let's swap it around and compare the right-hand side with the left-hand side. Problem solved. There is another alternative where we can do it with just one method, because now we had two. We had a freestanding method and we had a member method. That is with a technique called hidden friends. I always tell my colleagues, don't use friends. They are there to betray you. But in this case, it makes sense because we can really say this is part of the API of this class. It's not some other class barging in. No, it's closely related to the API of the class, so it makes sense. So we have, again, a function which now takes two magic ints. So not an int, but two magic ints. The benefit is now that the compiler can convert any integral int, first argument or second argument. So with one method, we solve the problem. Here we needed two methods, now only one. Problem solved. Well, problem solved for equality. There are more operators to have. Many of them we can implement in terms of the first two. Less than or equal, that's less than or equal. Not equal is not equal. Bigger than is actually not less than or equal, and so on. Let's implement them all. This is no rocket science. This is very trivial. It is cumbersome because I have a magic int class, but I have in the codebase many more classes like this where I need to do the same boilerplate. It is feasible and it works. It has done so since day one of C++. Yeah, these days we want to be complete. If it can't throw exceptions, we should add no except. Actually, we do want people, if you call this method, to not discard the return type. You would be surprised how many function calls are returning something and nobody looks at the return type. So we say, hey, if you're going to do that, the compiler is going to give a warning. And of course, we all use warnings into error, so the build will fail if you ignore the return type. And preferably, we make it const expr, because then it can be used at compile time. Now, all this decoration, again, we need to do it for every class in the codebase where we want this. All right, now let's enter the new era, C++20. C++20 has a feature which is called rewrites. What does that mean? For example, for the equality operator equals, and say we have two types and an instance type A and B. Suppose we write in the code, does A equals B? The compiler will try, as in the past, A equals B. Does that work? If not, if no such operator can be found or conversions cannot lead to such a finding, it's going to try, does B equals A? So where before we manually were swapping, the compiler is now doing this for us. I think that's a nice addition. what for A does not equals B? First, it's going to try, is there an operator? The not equal. If so, I will use that one. If there is no such thing to be found, it says, okay, let's try equals B and take the negation of that. If this is also not to be found, then the compiler says, let's try B equals A and take the negation of that. It will never try B does not equal A. Don't ask me why. It's not going to try this. These are the alternatives it's going to try. I think, again, this is a nice addition. There is less boilerplate for us to find. So let's look at our example. We have the magic int. We have the equality operator. The hidden friend is gone. So we just implemented the equality operator. We have a few magic ints, f1, f2. Is f1 equal to f2? No, it's not. Is it not equal? Correct. Is it equal to 2 for 2, or the other way around, is 2 for 2 equal to f1? Yes. This one is the method we had. 2 for 2 gets converted into a temporary magic int, and we compare. Here, the swapping is occurring. It's being rewritten as b equals a. Over here, f1 not equal to 2 for 2. There is no non-equality operator implemented. It is rewritten as not a equals b, and in this case, it's rewritten as not b equals a. So f1 and 2 for 2 are swapped, equality, and then negation. So that's good. Less stuff to write ourselves. Now, we're not even close to the spaceship operator. We like this functionality, so we say, yes, let's activate minus std equals C++20 on our code base and recompile the entire thing. The build breaks. That's good. We go for new stuff and our build breaks. Now, why is that? We have the regular equality operator on our class, and we had our extra freestanding method which allows to swap. Now, what's going to happen here is if you write this or this, there can be two options to choose from. You can go for the member method, or you could go for the freestanding method. Now, let's assume it goes for the freestanding method, which says, I will swap them around. So right-hand side equals the left-hand side. So you would think we will end up here then. No, we do not. Why? This requires a conversion. The integral int needs to be converted to a temporary. And the compiler says, I prefer swapping stuff than using a conversion. So the compiler says, okay, you swap them around, but I have two choices. I can go again for this one or for this one, and I need a conversion. Ah, no, conversion, that's worse. I'll go for this one. And we are swapping around forever. Compilers warn, so you can still build it and ignore the warning, but if you run it, it explodes. Anything can happen. So you activate this new feature, and you was eager to get it, and it breaks your code base. It doesn't build. So you need to solve all these issues. There is another warning I have seen. I did not put it in the slides, and that's ambiguity pops up. The compiler suddenly doesn't know, because it can do swapping, it has more options, and then it says, to me, this one and this one, they are on equal foot, and I don't know which one to use. That's another thing that can happen if you activate this in your build, that your build will break. Now, how do we solve this one? If you're only going to do C++20, you just remove this free method. That's the nicest refactoring there is. Throw away code. Just throw away less bugs. Or you say, well, I will help you out. I will force you to call the member method by calling it like this. Then the compiler doesn't need to say, I will swap. No. We are saying it's this member method, no discussion. I know better. That's one way to solve it. Another way to solve it is create the conversion first yourself, because then the conversion is done and there is only one viable solution anymore, the member method. So those are ways to solve it in case you say, yeah, we cannot activate the flag everywhere, or we cannot remove the code yet because it might still be built in an older version of a product where it's still C++17 or whatsoever. Of course, you can if-def. That's really the nicest solution, so don't go there, but it is a solution. All right. It's time to get to the spaceship operator, because that, in the end, was the title of this talk. Now, the spaceship operators, there are some rules to the game, and it depends if the spaceship operator is defaulted, as we saw in siblings in music. It was there, and at the end, it just said equals default, which means I'm telling the compiler, you implement it, and I'm happy with that, just like a default constructor. You say, I'm fine with whatever you come up with. Or it's not defaulted. We will see some examples why you would take matters in your own hands and not leave it up to the compiler. Don't call this yourself in code. Call the operators as we were used to, equals, less than, but don't call this yourself. This is actually an implementation detail. Of course, if you are implementing the spaceship operator for your class, then it makes sense that you might call the spaceship operator yourself on members of your class or your struct. Then it makes sense. Depending on the member support of your class, the spaceship operator will be const expr and no except. The rewriting rules that we just saw, for example, equality, also apply here if the first argument can be implicitly converted. So nothing new there. All right. The spaceship operator takes precedence over all other logical comparisons operator. So if you have A less than B spaceship operator C, it's first B spaceship operator C and then A less than. The return type of the spaceship operator is something that we will look at in a while. For now, it returns something. We saw in siblings in music, we used auto, so it returns something. At this moment, we don't know what, which can be compared to 0. That's it. So comparing to 0, what does that mean? Is it 0? Is it less than 0? Or is it bigger than 0? That's all we need to know for now. If you want to implement a spaceship operator, you have to include the compare header. All right. Let's revisit our magic int class, still with an implicit constructor. We say, okay, spaceship operator, return value auto. For now, we couldn't care less what it is. Take a magic int as constref. That's important. That's a signature. Constref, no, not by value, not ref, constref. That's it. It needs to be const, obviously. And we say, okay, compiler, you give me the implementation. I'm not going to do it myself. Here you see some little examples, F1, F2. We are comparing them, and we see the outcome. We can also have a vector and sort it. It works. So we did not implement equality operator. That's where we started in the past with, and the less than, because those are the two things you need to compare and to be able, for example, to sort in containers. No. This is the only line. And we get all 6 operators. We got the 4 relational ones, we got the two equality operators. It's defaulted. We say to the compiler, you generate the implementation for me. The compiler is going to compare member by member by member in the way it is declared in your class, in your struct. So order does matter. We saw surname, we saw first name. If you swap that around, this will behave differently. So order does matter. When you would not default it, you don't get the equality operators. Here the fun starts. It's not defaulted, and I lose the equality operators. It's a three-way comparison, like we know from string comparison. So that means if you have an operator A, operator B, it actually means A, operator B, less than 0, equal to 0, bigger than 0. That's what I said. The return type, it's something you can compare to 0. It's a three-way comparison. Oh, this is the more general notation. This is for the spaceship operation. Operator. Okay, the rewrites we saw in the beginning. Is x smaller or equal than y? If there is no matching definition, the compiler will now try, can I do x spaceship operator y less than 0? If that is not possible, because it's not defined, it will try, okay, is 0 less or equal than y spaceship operator x? Those are the rewrites. So x spaceship operator y equal to 0 means x and y are equal or equivalent. X spaceship operator y less than 0, it means x is less than y and similar for greater than. The not equal operator is never rewritten to call the spaceship operator. It could be it will call operator equal that was generated by the spaceship operator. If the members supported your class, the defaulted spaceship operator says it's const expr. We have a little struct, a coordinate, consisting out of 3 doubles, static assert. This compiles nicely, so it means it's const expr. Compiler was able to use the spaceship operator on this little struct at compile time. We didn't have to do anything for that. We also got this for free. Now, what if it's not defaulted? Let's take an example. We have a person which has a first name and a last name or surname, and we say on this struct, equality or the relation operators, it's only the last name that counts. First name, we couldn't care less. If it would be defaulted, it would be taken into account, either because first name came first, or if we swap the order of the two members, it still would take a role. So Michael Jackson and Janet Jackson would not be equal. If we skip the first name, then Michael and Janet Jackson would be equal because Jackson equals Jackson. So we implement the spaceship operator, and during its implementation, as said, then you can use the spaceship operator of the next thing. Because as said, it's an implementation detail. In your regular user code, you will not call it. But when you are implementing the spaceship operator, it makes sense to use it because you want to do the same thing you're trying to implement on one of your members. So this gives us the 4 relational operators. We don't get the equality ones. So that means if we would sort the characters of South Park, we could do that. If we would to check if the authors of South Park are equal to one another, it will not compile. Because it's not defaulted, we do no longer get the equality operator. So for that purpose, we also need to implement the equality operator ourselves and say, okay, last name equals last name. That's what we need. If the goal was only to get stuff sorted in the vector, you could say, I don't implement the equality operator. Of course, do as an int does. If you can compare an int, sort an int, then most probably your class should be able to be sorted and also to be compared for equality. So most of the time you want both. All right. Okay. So let's say we have our struct person, which has a last name, a first name. We added an age, and there was another member, some data. We don't care what it is. But in comparison, we don't want to take some data into account. So it's a bit similar as the thing we just saw before, where we were ignoring the first name. So it's not defaulted. We need to add the equality operator, and we can implement it by calling the spaceship operator on the members. Now let's see how that goes, because before we only had the last name, which was as a member to take into account. Now we will still have 3 members to take into account. So how does that work? Let's first start with the equality operator. That's easy. Is the first name equal and the last name equal and the age equal? The moment something is no longer equal, we bail out and we can say it's false. Spaceship operator. Signature as we are used to. We are saying now it's no except. We first check on the first member. That's our first criterion. What's the outcome of that? If it's not 0, we can return, because we know it's less than or bigger than the solution is already found. So if it's not 0, let's return. We know the answer. If the first member is equal, okay, we need to switch and inspect the second member. Similar thing. What's the outcome? If it's not 0, we know the answer. It's less than or greater than. And otherwise, we can return with the outcome of the third member. We have implemented this. Still, rather trivial code. And the data, we ignored that one. This is God knows what. Maybe it's some caching that makes views fail, as we have learned. Now there's another thing we should think about. Can we always compare things? Can we always order things? Is this possible? Another thing to think about, equivalence versus equality. An example, hello versus hello. We compare the strings, but we ignore the casing. These are not equal. I think we can agree on that. But if we would do a string case-insensitive compare, we would say, yes, they are equivalent. What do you do with doubles when not a number pops up? Here is a little example. D1, D2, and D3 is not a number. Is D1 equal to D3? To not a number? No. Okay, fair enough. Is it less than not a number? No. I think we know the answer. It must be greater than. Well, no. Nothing is less than, greater than, or equal to not a number. Not even, not a number. So this is weird. We want to compare stuff, and we have 3 possible outcomes normally, and none of them is valid. What's happening here? On the other hand, if I have D1, D2, and not a number, it's obviously D2 is less than D1. I put all 3 of them in a vector, and I sort. How the hell did this work? Nothing is less than, greater than, or equal to not a number. Nevertheless, it seems we can sort that, and that not a number seems to be on the higher end of things. That's thanks to the std less object. That's where the language puts in extra stuff in order to sort doubles. We have been sorting doubles in containers for ages, yes. So that's important. So when we want to compare things, we actually have different comparison categories. There are three of them. There can be strong ordering, there can be a weak ordering, and there can be a partial ordering. And in strength, they go from top to bottom. A stronger ordering can always be converted to a weaker one. So if something is expecting a partial ordering and I come with my, let's say, strong ordering, everything's fine. The other way around is not possible. So if something is expecting a strong ordering and I'm there with, let's say, a weak ordering, compiler says no. The return type of the spaceship operator, we haven't identified it yet. Auto, we said we couldn't care less. Well, the comparison category, that's actually the return type. And there are three different categories. So it means the spaceship operator can have one of these three return types. Let's have a look at strong ordering. Now, any value of a given type is either less than, equal, or greater than any other value of that type. So we can always compare. Some examples, integers, strings, and the return type is STD strong ordering, which is an enumeration. What are the potential values? Less, equal, or equivalent. They are the same or greater. So we will have, if it's a strong ordering, the spaceship operator will return something of type STD strong ordering, and it's one of these values. If it's a weak ordering, then any value of a given type is either less than, greater than, or equivalent. Not equal, equivalent. We already saw an example, case-insensitive string comparison. Return type is STD weak ordering. The enumeration values are less, equivalent, or greater. And then we have the weakest of them all, partial ordering. Any value of a given type could be less than, equivalent, or greater. Could. Could not is an equally valid option. Floating point types, Floating point types is an example. Return type is STD, partial ordering. It could be less, equivalent, greater, and when it can't be compared, it's unordered. So this return type has a fourth enumeration value that the other ones didn't have. Now, avoid writing code like this. Is the outcome of the spaceship operator strong ordering equal? This is correct code, but at a given moment, it might no longer compile. What if something of that type is changing on the inside? It might be it's no longer a strong ordering, but it was degraded to a weak ordering or a partial ordering. So don't do this. Write this. And you want to check, is it equal or equivalent? You just say, are you equal to 0? And as said before, typically you will not use that. You will use the normal operators. But in case you need that in implementation. So what if we change our person struct, we change the age to a double? Before it was an integer, now it's a double. We still don't care about some data. String, so that means strong ordering. Double, partial ordering. Now what is the return type of our spaceship operator? Is it a strong ordering? Is it a partial ordering? Or do we have some complex rules that turn it into some other ordering type? The complex rules are not there. That's good. Could we say, let's ignore this fact and still put auto? No, we can't. Why? We saw before our criterion 1, blah, 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 return, criterion 2, return, and then return on the last criterion. It means we had 3 different points in the code where we can return. Now, auto can deduce the return type, but there is one condition. Every return point, return statement, should return the same type. You cannot say, on line 5, I will return an int, and on line 7, I will return a string. Or put here, you cannot say on line 5, I return a strong ordering enumeration value, and on line 7, I will return a partial ordering enumeration value. So we cannot rely on auto and trying to ignore the problem. So what can we do? We know that stronger comparison categories can always be used if you need a weaker one. So we could say, okay, let's go for some common ground. Let's go for the weak type. So we say it's going to be partial ordering. We compare the strings. Comp at this moment is a strong ordering. If it's not 0, we already know the outcome. So we are returning a strong ordering, which can be converted into partial ordering. This is all okay. And then at the very last line, this we know that's the double. This is going to be a partial ordering, which is an exact match of the return type that we have specified. Or we could say, I like the strong ordering. I will convert it, the partial ordering member, I will convert it myself to a matching value of the strong ordering type. Might make sense, it might not make sense. It all depends. So the first mappings are trivial, less will be less, equivalent will become equal, and greater will become greater. The question is, what do we do with the last one, the unknown value? Partial ordering, there was enumeration value unknown. Just for the stupidity and sake of this little example, we say, okay, unknown, we turn it into a less. So we solve the problem by saying the weaker one, we ourselves will map it to something that makes sense to us. When it's about doubles, the language can help us out. We want to go for strong ordering. We can say, when we compare the double, use std strong order on the two things, the two doubles we want to compare. This also works for not a number. We saw before how was it possible that the doubles could be sorted in a vector because of std_less, a function object. There is a similar function object compare three-way, which does the same thing here for doubles, and the comparison of doubles is a strong ordering. So the language comes out and helps us for doubles. Templates, generic code. What if we don't know what the types are? Before we knew it was a string and it was a double. But I'm writing generic code. There are two types in my struct. I want to implement the spaceship operator, but type 1, what ordering category? We don't know, because we don't know what type 1 is. The same for type 2. They could be both strong ordering, both partial, or a mix. What should it be? Now, we can determine the common ground by std common comparison category of type 1 and type 2. And it will compute what it is. And we don't further take notice of the thing. It's being done for us. Here is an example. Of course, here it are still concrete types, but imagine this would have been in template, and T1 and T2 that came in the template would be string and double. Spaceship operator, we still say auto, but we use the trailing return type. STD, common comparison category of decal type, name, spaceship operator, name, and decal type, value, spaceship operator, value. Now, you might wonder, shouldn't this be right-hand side name? No, doesn't matter. It's just the type of this comparison we want to know. It's something is determined at compile time. Nobody is comparing values over there. So that's why I just wrote name, spaceship operator, name. So this would be the strong type, strong comparison. This would be the partial one. Common would be partial one. So it would be a partial ordering. The rewrites, suppose we want to call x not equal to y. The compiler will try again some rewrites. First of all, it's going to see, is there a not equal operator in the type of x? If that is there, it will use it. If this cannot be found, second thing to try is there a freestanding not equality operator taking an x and a y? If that is not there, next thing to try, let's try the equality operator on x taking a y and take the negation. Or if that's not there, try a freestanding equality operator taking an x and a y and negate. If that's not there, let's see if there is an equality operator on the y type taking an x or something that can be converted to an x and take that. If that also does not exist and the spaceship operator would exist, let's see if there is an equality operator on the type x taking a y that was generated by the spaceship operator. And if that's not available, let's try the similar thing of the generated thing of the spaceship operator on the type y. So that means I can have the spaceship operator and in the end have implemented one of the functions myself. So let's say I have implemented the spaceship operator on my type, and I also implemented the less than operator. So that means in the end we would have two, the one generated from the spaceship operator and the one that I implemented myself. The one which was implemented by yourself takes precedence. That's why we also first say, let's see if it exists made by the programmer, and only at the end, if it's not to be found, and there is a spaceship operator which allows it to be generated. Sometimes equality is not there if it's not defaulted. That's the way it works. Yes? Equality operator. So I will repeat the question. The bottom two are only there when the spaceship operator is not defaulted. Yes, that's correct. If it's not defaulted, they are not there. Then you have to explicitly add it yourself. That was equality. Now let's go for the relational operators or the spaceship operator by itself. X less than or equal than y. First thing the compiler will try is this less than or equal operator on the type X available taking a y? If that's there, that's what we use. If it's not, is there a freestanding operator less than or equal taking an X as the first argument and taking a y as the second argument? Knowing that the freestanding, both operands can be converted. We saw that with the int and the magic int. If these are not there, okay, Let's try the spaceship operator on x taking a y, and is it less than or equal than 0? If that is also not available, let's see if we can find a freestanding spaceship operator taking an x and a y. If that is also not there, then let's try the spaceship operator on the y type taking an x, but then it's greater than or equal to 0. Okay, concepts. Say we have a method foo that needs a type T, and somewhere in the implementation we will use a spaceship operator. So this is a requirement. We should make sure that types that come in fulfill this requirement. In the past we didn't have that. We could std enable if or whatsoever, or we go for big compiler error messages, whatever. So what if we want to do it with concepts? Then we say, okay, we require, and there is a concept for that, three-way compatible. So we have our magic int, we have our non-defaulted int, both are three-way compatible. This one got all 6 from the spaceship operator. This one got 4 because it was non-defaulted, but we added the equality operator. So both fulfill the requirement to be able to call foo method.
Those safety things are kind of the same for most of them.
Let's look at an alternative and let's play around a bit with concepts. Suppose we would handcraft this and not use the existing concept. We want a spaceship operator, and maybe we also want the equality operator. In this example, we just say it's my space shippable, and we have a required expression. On a T, we should be able to compare, or spaceship compare T. So T spaceship T. Again, this is just to see if this compiles. So I'm not saying T1 versus T2. No, T versus T is sufficient in order to see if this compiles. So our magic int, which with the defaulted, obviously is okay. The non-defaulted int is also okay because we only say we want a spaceship operator. We are not checking here that the equality operator should join the party. If we handcraft it and we want all 6, we should also add T equals T. Of course, don't do this yourself. There is a concept. Just, let's say, a little concept, 101. Another way to write it, again, it's more about concepts 101. You could say equality compatible. That's also an existing concept. And then we say, okay, and we also want something else. We want it to be spaceship. Spaceshipable. I don't know if this is a new verb or adverb. Okay. One more thing, inheritance. First, the base classes will be compared from left to right. So D derives from base 1, comma, base 2, base 3. We'll first check base 1, then base 2, then base 3. Now, if we say the derived class is defaulted, that only means that the members in the derived class can be compared. Doesn't mean that the base class is automatically also defaulted. No. You only defaulted comparison of your derived class. So that means that the base class should provide all the needed operators out of the list of 6 also. That's the base class responsibility. Because we say our derived class D is defaulted, it doesn't say anything on the base class. So if the base class does not provide it, and you say, as a derived class, I am defaulted, something is going to go wrong because it wants to compare the base classes and it will see, oh, there was no equality operator on the base class. Computer says no.
This is very good. It's just like one tiny percent of the cases.
So a very trivial example, we have a base class. We add the spaceship operator as defaulted. We need to add it. The derived class, we also add it. And then we can play around with it. D1 equals to D2, yes or no. D3 versus D4 will be. So this one will be different because the derived part is not the same. This one will also be not equal because the base part is not the same. And over here it is equal. And now this is really the end of my talk.